Today's topic is on atoms, charges, and the Coulomb force law. If you take a look at the picture behind me here, it's multiple lightning strikes occurring over the ocean. You know, lightning strikes, as exciting as they are just as dangerous. But lightning strikes, they've got a story that goes back a very long time, to the days of antiquity. You know, the ancient Greeks, for example, attributed lightning strikes to Zeus. The Romans, during the run of the Roman Empire, the Romans attributed this to Jupiter. Even the Germanic tribes, the folks of Scandinavia, attributed lightning strikes to Thor. So different cultures in different generations over thousands of years, they've held lightning strikes in great reverence. Although I assume none of them understood what was actually happening, so they had to attribute this to something else. But lightning strikes are quite fantastic, in this chapter, the work here deals with everything that goes into creating something like this, like a lightning bolt. A single lightning bolt contains enough energy that if we could build a battery that wouldn't fry, that could store all of the energy from a single lightning strike, we could probably power the United States for years just on a single lightning bolt. But that technology hasn't caught up yet. But no, more to come on that. Now, if we were to look at the chapter, the chapter deals with a bit of the history of the discovery, if you will, of electric charges. It actually goes all the way back to ancient Greeks, when they would take tree sap, a type of tree sap that hardened. It's called amber. As a matter of fact, the word electron is the Greek word for amber. So they would rub this amber with different kinds of materials like cloth and fur and silk, and they would notice that there would be some kind of an attractive force holding the two together where they would cling to each other. And that was the earliest signs of the attractive nature of materials. So we know today that materials can either attract or repel each other. So far removed from the days of antiquity, from the early Greeks with their play with amber, we moved to the 1700s, to the days of Benjamin Franklin and the people that came after him. Benjamin Franklin was the first to introduce the concept that in all of nature there are just two kinds of charges, which he arbitrarily labeled as positive and negative. Then it wasn't until after him, and that people like J.J. Thomson and Ernest Rutherford, Robert Millikan, Charles Coulomb, they all contributed in one way or another to the actual discovery of the electron as a particle by itself. Then someone had to measure the actual charge and the mass of this electron. It turns out the electron is the fundamental unit of charge. Nothing else exists that has a small charge that is stable, that can exist by itself. So it is the fundamental charge in all the universe as far as we know. Everything else is built on this building block of one charge of the electron. We know today it's given the value of a negative charge of 1.6 times 10 to the negative 19th Coulomb. The Coulomb is named after Charles Coulomb. But much more of such details and historical aspect of the discovery of the electron and its properties in the chapter. That's left for the reader to entertain themselves with. But in this chapter, we talk not just about the electron, but of all of the fundamental particles, the protons and the neutrons that go up into making up an atom. And it turns out that the protons and the neutrons, as the reader will find out, are not truly fundamental. They're actually elementary charges that make up the protons and the neutrons, things that are much, much smaller than the protons and the neutrons. These are things called quarks. The quarks are quite weird. They've got a fraction of electronic charge, and they can either be up or down, and it gets very complicated. But a little bit of that is delved into, so it sort of starts the book, if you will, from chapter 1, not in the middle of the book at chapter 12. So the reader has an idea of where everything fits into the grand scheme of things. There's coherency taking from the very, very small that we know of and building to something larger and larger and larger as we go along. So the idea is to get coherency, not to get complicated. to start at the beginning, not somewhere in the middle. No. So as we go along, we talk about the Coulomb force law. So this is the basic force law of attraction and repulsion. And so it's as simple as two charges, like two electrons. Same charge, negative, they're going to repel each other. But if we were to consider a proton, which has the same magnitude but opposite sign of charge compared to that of electron, we get an attractive force. And for the sake of comparison, I did an example here where we looked at the attractive force between a hydrogen, or rather a gold. To start off, we use gold between the nucleus of a gold with 79 protons and one of the electrons close to the nucleus, and we calculated using the Coulomb force law what this force of attraction would be, and then did a second calculation on the repulsive force between the similarly charged protons. They're all positive inside the nucleus. That's a repulsive force. So we compared the two forces, the one of attraction and one of repulsion, and to understand which one dominates and how significant it can be. And there are startling revelations made out of this, by the way, that the repulsive force that's trying to rip apart nucleus from the inside out is very, very, very strong. So there had to be something else that is much stronger than that repulsive force that's holding the nuclei of every atom together. It turns out that's one of the other fundamental forces, the strong nuclear force that overwhelms the electrostatic force. But the strong nuclear force, even though it's very, very strong, it only acts for very, very short distances, maybe a billionth of a meter or less. So the larger atom that you have, it becomes so large, the atom, the nuclei, that is, that the strong nuclear force begins to fall off exponentially with the increasing size of the nucleus. And then the electrostatic force of repulsion between the protons takes over, and the electron becomes unstable, and radioactivity sets in. So even radioactivity can be explained in terms of the force of attraction, repulsion, and which one wins and which one loses. But more about this chapter. Here's a picture of me as a PhD student in physics using an STM, a scanning tunneling microscope. So where I did several years worth of experiments, and this chamber over here is a high vacuum chamber where the air is sucked out, and I was able to use the scanning tunneling microscope. It's based on the quantum mechanical principle of tunneling. That is, if you were to bring two electrons close together, they have what are called wave functions, and they overlap. And the overlapping of the wave functions create a highway, if you will, for charges to flow and generate an electric current. And that electric current is measurable. It's very, very, very small, billions of a volt, but it's measurable. And these are some of the images that I took of the surfaces of gold using that device, that scanning tunneling multi-million-dollar equipment over there, that microscope. And I took a small piece of gold, much smaller than the size of my pinky nail here, and I kept zooming in and taking deeper and deeper and deeper pictures. These are large terraces of the gold. I put this up for comparison to give the reader an idea of not just how small things are, but they have their own world when it comes to such small things. And as we zoom in more and more and more, every little dot that you see here, this is a picture that is about 4 billionths of a meter by 4 billionths of a meter that way. And each little dot that the reader sees is an individual atom. Atomic site. It's actually an electron. Each little dot that's lit up. So it's actually a picture of the atomic structure of gold, which is quite fascinating. And this is even a deeper scan. It's actually less than 1 billionth of a meter across. And so it zooms in even more on the periodicity, what's called a herringbone structure of gold. So I thought the reader might find that interesting. It's difficult to talk about something you can't see, but now you can, thanks to, well, me taking these pictures over here. So many calculations are done in this chapter of looking at the magnitude and the direction of the charge, that is the force vector, the Coulomb force vector between different kinds of discrete charges. And I've used several examples of putting charges, negative and positive, on the x and y coordinates and calculating what the net force would be on any randomly chosen charge. So the reader can have many examples to look at, and you can see that it gets quite detailed in the calculations. There's a lot to follow, certainly more than I can go over in this brief introductory video to the chapter. It's left for the reader to spend a lot of time on. But as we go through, we talk about the concept of an electric dipole. Electric dipole, for example, water. The water molecule. Water is quite fascinating. We can talk for days just in something as mundane, seemingly mundane and popular and ubiquitous as water. But water is really, really fantastic. It has some properties that it's truly unique just to water. One of these properties of water that's not so unique, but it's a property of water, is that it takes H2O. It takes two hydrogen atoms and one oxygen atom to form an oxygen hydrogen molecule, a water molecule. It turns out that the electrostatic force of the oxygen nucleus contains 8 protons is stronger on some electrons that are being shared between the hydrogen and the oxygen. So the hydrogen now, it only has 1 proton, and so it has the weaker pull than the 8 proton nucleus of the oxygen atom. So electrons that are being shared, these are called covalent electrons, that creates the bond, the glue, if you will, that hold the water molecule together. The pull is stronger towards the oxygen side. So the oxygen side is a bit more negative than the hydrogen side. So you have an overall molecule that has a discrepancy of charge. It's called electronegativity. And so the oxygen side is more negative than the hydrogen side. And this is what's called a dipole. So with dipoles, many molecules in nature are dipole like that, where they have a segregation of charge within a single molecule. And so dipole molecules will only interact with other dipole molecules, and all kinds of things come out of this. Surface tension of water, for example. How certain animals, very lightweight, can walk on the surface of water. That's because of the surface tension caused by these dipole molecules interacting. This is how detergent can remove organic residue, oil and grease and dirt and stuff from your hands, polar molecules interacting. So there are many everyday examples of the interaction of dipole molecules with their same kind. And so several of them are done in this chapter. So here's a picture of some dog sledding in the far north and close to the Arctic Circle in north of Sweden in the middle of wintertime. And this is an example of looking at a water layer that's melted in the ice, and how ice differs from the water molecule, how the dipole forces are different and the electrostatic forces are different. So it doesn't matter if you're close to the North Pole like I am here in dog mushing in the Arctic north of Sweden, or if I am exactly in the opposite pole. This is Antarctica and all of the ice in Antarctica. The ice actually takes on different constituencies, different constituents, as it's molded together under extreme weight of successive snowfall. So the ice and the bonding features and strengths take on different properties as we go. Here's some more ice in some ice caves in Austria, and Werf in Austria. This is unique to these caves over here, how the frozen waterfalls get formed. And so this is the structure of how the dipole molecule, the water molecule, is formed, and how ice can also form as well. The difference between the bonding between the water and the ice, and even the gaseous form, the water vapor form, that's also dealt with as well. Like every chapter, there are multiple examples to keep the reader busy for quite some time, and this chapter is no exception. Some additional problems on calculating the net electrostatic force on a single charge when it's in the neighborhood of other discrete charges. Okay, so at the end of this chapter, the reader should have a good knowledge of the history of the discovery of the electron and the properties of the electron and who made what contribution. The water molecule, the structure, the tetrahedral structure of the water molecule, and how it bonds to itself and other things as well. And fundamental knowledge the reader is going to get of the electrostatic force of attraction and repulsion. All right, once again, I thank you for your time.